problem, right? Well, it's not a third order problem. This is a first order problem with 3 separate first order problems, right? To solve this is to find 3 functions that simultaneously solve all 3 of these differential equations at once, right? That's the goal. One more reduction of order example, and then I'll share with you the method. Just the all right, so here's another one. We could have y prime 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 plus 3y prime prime plus 3y prime plus y equals to 0. This is a third order constant coefficient ordinary differential equation. In fact, we can solve this, but I'm not going to do that. Instead, I'm going to write down x1 equals to y, x2 is y prime, x3 is y prime prime. We can use this as reduction of order for this third order problem, like this. So you see we get x1 prime is what? x2 prime is what? x2, x3. And what is x3 prime? It is y prime prime prime, also known as, from this up here, minus 3y prime prime minus 3y prime minus y, aka minus x1 minus 3x2 minus 3x3. So if you put this into a matrix, 1, 2, 3 prime equals what matrix times x1, x2, x3. What's the corresponding system of, what's the matrix? We're trying to find the standard matrix form of the corresponding system of 3 first order differential equations. All right, that's my current aim here. So we got what? We got, I'll let you guys catch up. What we got? 0, 1, 0. We have winner. Next up, 0, 0, 1. Next. Negative 1. Negative 3. Negative 3. There you go. So this is the matrix of coefficients for the system. And so this third order differential equation is equivalent to, you know, dx dt, dx vector dt equals to ax, where x vector is x1, x2, x3, as we've just defined. All right? Now you might say, well, that's kind of silly. I already know how to solve this problem. Why would you do this? I'm doing it to illustrate the method. What I want to convince you of, and I'm not going to prove this because no one wants to see that, is that if we have any collection of linear differential equations that could be like second order, third order, fourth order, whatever, you see we can keep doing this for like a fifth order problem, right? We just would introduce x1 is, you know, x1 is y, x2 is y prime, x3 is y prime prime, and x4 would be y prime prime prime, x5 would be y. You get the idea. We can keep reducing order for arbitrarily high, and we can do this for every one of the differential equations we have. And if you put that all together, at the end of the day, a system of linear differential equations can always be reduced to a problem of the form dx dt, right, equals to ax. This is, you know, n first order ODEs in matrix standard form, all right? We can always put a system of linear differential equations into this form. Yeah.
Is there only one solution for the matrix A, or is that just the best solution?
Oh, yes, there are infinitely many different choices of A, absolutely. So that was a very ad hoc choice on my part, you know, to make x1 and x2 and x3 as we did. You're right, we could have done other things. And yeah, you're right. So what I'm just showing you, like, you know, a standard choice is all. So I want to talk to you guys now that you understand the problem, I want to show you the solution. All right, so how do you solve this? How do you solve dx dt equals to ax? All right. Now you might say, we only have 5 minutes of class left, so there's no earthly way that you can possibly describe how to solve a matrix system for an arbitrary matrix in that amount of time. But in fact we can, because the matrix notation is just that concise. So here's our goal. Solve dx dt equals to ax, all right? What we're going to do is we're going to guess solution of form x vector equals to e to the lambda t times a constant vector u. Right? So I'm saying lambda is a constant and u is a constant vector. That's a reasonable guess to make because e to the lambda t served us well. So we should try multiplying that by a vector, see if it works, right? Does it work? I don't know. Let's find out. What's dx dt? U is a constant vector. I can pull it outside the differentiation, right? What's the derivative of e to lambda t? Lambda e to the lambda t times u. All right. This has to be equal. If it's a solution, what does it have to do? This has to be equal to what? Ax, right. But this, for our x, is a e to the lambda t times u. See? This is what we must solve in order for it to work. So we have this is equal to that. E to the lambda t is never 0, right? It's never 0. So what that means, if I can flip the script here a bit, is a times u has to be equal to lambda times u. But let me rewrite that just a little bit more. A minus lambda times the identity matrix times u has to be equal to 0. The identity matrix, the matrix with ones down the diagonal, as you study matrix multiplication, I'll give you homework on this. This is easy homework. You can prove that the identity matrix times any vector just gives you back the vector again, all right? So if I've got lambda times u, I can rewrite lambda times u literally as, lambda times the identity matrix times u. That's just an identity, all right? So this is equivalent to that, right? Do we want u to be 0?
No.
If u is 0, we've got the 0 solution, right? Is 0 a solution?
Yeah.
It is a solution. Is it the one we were interested in? Not really. So we don't want the u vector to be 0. What does that say then? So we look at this, right? We need u not equals to 0. So if I let the matrix B, for the sake of discussion, be equal to A minus lambda I, right? What can you tell me about this matrix? No, well, it's not, but it's not the 0 matrix, no. It's a matrix which has u not equal to 0 as a solution, right? Like b times u is equal to 0. What else is 0? How about this? B times the 0 vector is also 0, right? What did I tell you earlier today? If you have a matrix and you look at the homogeneous equation, right, the matrix times the vector equal to 0, and you have more than just the 0 vector, it must be that that matrix is not invertible. This forces the determinant of B, this right here, since u is not equal to 0, forces us to say that the determinant of B is equal to 0.
Therefore, it's not invertible.
The matrix B is not invertible. So what we need is that the determinant of a minus lambda I has to be equal to 0. This, by definition, is the so-called characteristic equation. The characteristic equation for A. The solutions to the characteristic equation are called eigenvalues. Lambda is called an eigenvalue. Lambda is an eigenvalue. I call this solution that we constructed right here, I refer to this as an eigensolution, because what you're looking at is e to an eigenvalue times time times u. By the way, u is called an eigenvector. So in short, if we can find eigenvalues and eigenvectors for our matrix, we find solutions to the system. This is a path through the wilderness which does not require any kind of clever substitutions. It's just an annoying calculation, which we will get into next time. All right? So, anyway, that's all I got. Go home now. or go get some lunch or something. I don't know, whatever, but